Hello friends, welcome to my second lecture on assignment problem. Let us discuss maximization of an assignment problem. We have earlier discussed in the previous lecture minimization problem. Now we consider maximization assignment problem. So sometimes the assignment problem deals with the maximization of the objective function. That is, the problem may be the problem may be to assign persons to the jobs in such a way that the expected profit is maximized. Such maximization problem can be solved by converting it to a minimization problem, and it can be done by converting the profit matrix to the cost, or that is loss matrix. There are two ways to do this. Okay, it can be done in two ways. The first way is subtract each element of the given matrix, that is profit matrix, from the greatest element of the matrix to get the equivalent cost, that is loss matrix. Okay. The second way is place minus sign before each element of the profit matrix to get the equivalent loss matrix, and then we apply the usual Hungarian method to obtain the solution of the assignment problem. So, let us consider this problem. Alpha Corporation has 4 plants, each of which can manufacture any of the 4 products. Production costs differ from plant to plant, as do sales revenue. From the following data, obtain which product each plant should produce to maximize profit. So, this table first table gives us the sales revenue in thousands of rupees, and the second table gives production cost in thousands of rupees. Okay. A, B, C, D are the 4 plants, okay, and there are 4 products 1, 2, 3, 4 which are manufactured by the 4 plants. Now, we know that profit is equal to sales revenue minus product cost. So, the matrix of the profit matrix is as follows. We can subtract from the sales revenue the product cost. Okay. That is, we can subtract this matrix, okay, second matrix, from the first matrix. So, 50 minus 49, that is 1, 60 minus 55 is 5, 55 minus 52 is 3, 58 minus 55 is 3, and so on. Okay. So, this matrix, from this matrix we subtract this matrix, second matrix, to obtain the profit matrix. Okay. So, this is our profit matrix: 1841, 5765, 3542, 3163. Now, we have to maximize the profit. Okay. So, this is a maximization problem. Okay. We shall solve this problem by converting it to a minimization problem in both the ways we have discussed. Okay. Let us consider the first way of converting it to a minimization problem. Okay. So, in the first way, what we do, we subtract each element of the profit matrix from the greatest element of the profit matrix. Okay. So, the greatest element of the profit matrix, you can see there are 4 by 4, that is 16 elements. Of those 16 elements, the element 8, okay, is the greatest element. So, we subtract each element of the given matrix from the greatest element. Okay. So, 8 minus 1 is 7, then 8 minus 8 is 0, then we have 8 minus 4 is 4, 8 minus 1 is 7. So, first row is 7047, second row 8 minus 5 is 3, 8 minus 7 is 1, 8 minus 6 is 2, and then 8 minus 5 is 3. So, we get the second row as 3 1 2 3, okay, 3 1 2 3, and then similarly third row becomes 5 3, okay, 4 and 6. So, 5 3 4 and 6, and the fourth row becomes 8 minus 3, that is 5, 8 minus 1 is 7, 8 minus 6 is 2, and then 8 minus 3 is 5. So, we get 5 7 2 and then 5, okay, 5 7 2 5. So, this is now the loss matrix, okay, which we have obtained by subtracting the elements of the all the elements of the profit matrix by the greatest element of the profit matrix. Okay. Now, what we will do, we will apply the Hungarian method, okay, as we have discussed in the last lecture, okay, to arrive at the solution of the problem. Okay. So, now it is the minimization problem. So, as we did do in the Hungarian method, okay, from the 7404 we will find the smallest element of the first row. The smallest element of the first row is 0. Okay. So, we subtract 0 from the all the elements of the first row and we get 7047. Okay. So, 7047, then we subtract the smallest element of the second row from all other elements of the second row. So, 1 we subtract from 3 we get 2, then we get 1 minus 1 0, then 2 minus 1 is 1, then 3 minus 1 is 2, and then the smallest element of the third row is 3. So, 5 minus 3 is 2, 3 minus 3 is 0, 4 minus 3 is 1, 6 minus 3 is 3. The smallest element of the fourth row is 2. So, we subtract 2 from 5 to get 3, and then 2 we subtract from 7 to get 5, 2 minus 2 is 0, okay, and 5 minus 2 is 3. Okay. Now, the same thing we do for all the columns. So, in the first column the smallest element is 2, okay. We subtract 2 from all the elements of the first column and we get 5, 0, 0, and then we get 1. Okay. In the second column the smallest element is 0. So, when we subtract 0 from all other elements of this column we get the same elements. So, 0, 0, 0, 5. Okay. Similarly, in the third column the smallest element is 0. So, subtracting 0 will not change it, 4, 1, 1, 0. Okay. In the fourth column the smallest element is 2, subtract 2 from all the elements of the fourth column we get 5, we get 0, we get 1, we get 1. Okay. So, this is the reduced matrix. Okay. And then we start from the first row. In the first row we have a single 0. Okay. So, we encircle it and then cross all zeros which lie in its column. So, we cross these two. Okay. Then we go to the second row. In the second row we have 2 zeros. Okay. In the third row we go to third row we has got 2 zeros, third row has got a single 0. So, we encircle it and then cross the zeros which lie in its column. So, we cross this and then we go to the fourth row has a single 0, we encircle it. Now, we go to the first column. Okay. First column has been there is no 0, this 0 has been assigned. In the second column there is no 0, this 0 has been assigned. In the third column 0 has been marked. In the fifth column, in the fourth column we have a 0. So, we make an assignment here. Okay. So, now the first row has an assignment, second row has an assignment, third row has an assignment, and fourth row has an assignment. Okay. So, this gives the solution of the problem. Okay. So, this means that A, B, C, D plants are there, okay, and products are 1, 2, 3, 4. Okay. So, A goes to 2, okay, the plant A, okay, plant A will produce product 2, okay, plant A will produce product 2, plant B will give product 4, and plant C will get product 1, and plant D will get product 3. Okay. So, when A is given the product 2, B is given the product 4, C is given the product 1, and D is given the product 3, then the profit will be the maximum. Okay. So, you can see here A is getting the product 2, B is getting the product 4, C is getting product 1, D is getting the product 3, and the maximum profit, as you can see from this table, A is getting the product 2. So, the profit is 8, okay, and it is in thousands. Okay. So, it will be 8,000. Okay. So, 8,000 and B gets 5, this is 5, okay, and C gets 1. Okay. C gets 1. So, this is 3 and D gets 3. So, this is 6. Okay. So, profit, maximum profit will be equal to 8 plus 8,000 plus 5,000 plus 3,000 plus 6,000. Okay. So, 6 plus 3 9, 9 plus 5 14 plus 8 22. So, we get 22,000. Okay. So, if A is given the product 2, the plant A is given the product 2, plant B is given the product 4, C is given the product 3 and D is given the product of 3, then the profit will be the maximum and it will be rupees 22,000. So, this is how we solve this problem of on maximization of profit. Now, let us go to the second method. In the second method, what we do is we put the negative sign before each element of the profit matrix. So, this is our profit matrix. Okay. This is our profit matrix. We put a negative sign with each element of the profit matrix, then it will be -1, -8, -4, -1, -5, -7, -6, -5, -3, -5, -4, -2, -3, -1, -6, -3. So, the equivalent loss matrix, the matrix which is the loss matrix will be this one. Okay. After we put a negative sign with each element of the profit matrix, we arrive at this matrix. Now, what we will do, we will apply the Hungarian method. So, we subtract the smallest element from each element of the first row. Okay. So, smallest element is -8. So, -8 we subtract from each element of the first row. So, -1 plus 8 is 7, -8 when we subtract from -8 we get 0, -4 plus 8 is 4, -1 plus 8 is 7. In the second row the smallest element is -7. So, -7 we subtract from -5 we get 2, -7 when we subtract from -7 we get 0, -6 plus 7 is 1, -5 plus 7 is 2. And here the smallest element in the third row is -5. So, -3 plus 5 is 2, -5 subtracted from -5 gives 0, -4 plus 5 is 1, -2 plus 5 is 3. In the third row the smallest element is -6. So, -3 minus -6 is 3 and then -1 plus 6 is 5 and then -6 subtracted from -6 gives 0, -3 plus 6 gives 3. Okay. Now, let us subtract the smallest element from all other elements of each column. Okay. So, smallest element in the first column is 2. Okay. So, smallest element 2 we subtract from all other elements of the first column, we get 5, 0, 0 and then we get 1, here we get 0, 0, 0 and 5, okay, because the smallest element is 0 and 4, 1, 1, 0 and we subtract the smallest element 2 here from all other elements here. 7 minus 2 is 5, 2 minus 2 is 0, 3 minus 2 is 1, 3 minus 2 is 1. Okay. So, this is our reduced matrix. Okay. And then the same reduced matrix we had got here, you can see the same matrix we had got here. So, we follow the Hungarian method, we arrive at the same solution. Okay. So, same matrix we get. Okay. So, we follow the Hungarian method and we get the same solution as in the case as in the first method, that is A is given the product 2, B is given the product 4, C is given the product 1 and D is given the product 3. Okay. So, this is what we get, which is the same matrix as obtained in step 1 and 2 in the wave 1. Now, hence giving 0 assignment we get the same optimal solution as by wave 1. Okay. Now, restrictions on assignments. Sometimes due to some restrictions the assignment of a particular facility to a particular job is not permitted. Okay. To overcome this difficulty, a very high cost, that is infinite cost, is assigned to the corresponding cell, which automatically excludes this activity from the optimal solution. Okay. So, if there are some if they due to some restrictions the assignment of a particular facility to a particular job is not permitted, then we will apply we will assign infinite cost to that cell, okay, and which will exclude that activity from the optimal solution. So, let us see how we do this. For example, let us consider this problem. Okay. So, here we have this is an unbalanced problem. You can see we have this is a 4 row, okay, 4 rows are there and 5 columns are there, 5 columns are there, and due to some restrictions C and this one third this one, okay, these two cells, this cell and this cell, okay, are not assigned any cost. Okay. So, they will be giving infinite cost to them. Okay. So, the facility is not assigned to the particular facility is not assigned to a particular job. Okay. So, these are blanks here, we will assign infinite cost to them, and to make it a balanced problem we will add one dummy according to the given assignment table facility B. Okay. These are facilities. Okay. These are facilities. So, as facility B cannot be assigned to job 3. Okay. These are jobs. Okay. So, according to the given assignment table facility B cannot be assigned to job 3 and facility C cannot be assigned to job 1. So, we can assign a very high cost, that is infinity, to the cells B 3 and C 1. This is B 3. Okay. This cell is B 3. Okay. And C 1, this one is C 1. We assign infinite cost to these cells, and also the matrix is not a square matrix, that it is not, it is an unbalanced assignment problem. So, we add a dummy facility. Okay. We add a dummy facility E, okay, with 0 cost in all cells of this row. Okay. We give 0 cost to all cells in this row, then we get the following assignment table. Okay. So, now this has become a balanced problem. Okay. We will subtract the minimum element of each row from every element of the corresponding row, and then subtract the minimum element of each column from every element of the corresponding column. So, if we do this, then what will happen here? Minimum element of the first row is 9. Okay. So, 9 we subtract from every element of the first row, we get 0, 2, then we get 6, we get 1, and 11 minus 9 is 2, and then here we subtract the smallest element 9 from every other element. So, we get 3, then 0, then we have infinity, infinity minus 9 is infinity, then 10 minus 9 is 1, and then 9 minus 9 is 0. Here the smallest element is 7. So, infinity minus 7 is infinity. So, 11 minus 7 is 4, 14 minus 7 is 7, then 11 minus 7 is 4, 7 minus 7 is 0. Then the smallest element in the fourth row is 7. So, 14 minus 7 is 7, 8 minus 7 is 1, 12 minus 7 is 5, 7 minus 7 0, 8 minus 7 1, and the last row is the same, because smallest element is 0 subtracted from all other zeros gives 0. Okay. Now, we do the same thing for all columns. So, smallest element in the first column is 0, which when we subtract from all other elements we get the same element. Here we smallest element is 0. So, it subtracting it from all other elements does not change it. Here again smallest element is 0. So, when it is subtracted from all other elements it will not change. Here also the smallest element is 0. So, the column remains the same, and here also the smallest element is 0. So, this is now reduced matrix. Okay. So, we get the reduced matrix as 0 2 6 1 2, 0 2 6 1 2, 3 0 infinity 1 0, 3 0 infinity 1 0, infinity 4 7 4 0, infinity 4 7 4 0, 7 1 5 0 1, 7 1 5 0 1, and then last row is 0 0 0 0 0. Okay. So, this is our reduced matrix. Okay. Now, we begin with row 1. So, in row 1 we make an assignment here, because there is a single 0 here, and then cross out all zeros which lying in its column. So, we cross this, we go to the second row has got 2 zeros. Okay. So, we move to the third row has got a single 0 here, we make an assignment here, and then cross out 0 and this 0 which lie in its column. In the fourth row there is a single 0 here, we make an assignment here, and then cross out a 0 which lie in its column. Okay. And then in the fifth row we are having 2 zeros. Now, we go to the columns. Now, let us consider the columns one by one. Okay. So, in the first column there is no 0 which is left. Okay. In the second column we have 2 zeros, in the third column we have a single 0. So, we make an assignment here, okay, and then we cross out this 0, okay, which lies in its row, okay, and then we go to a fourth column. In the fourth column there is no 0 here, and then in the fifth column there is no 0 here. Okay. So, what we have in the first row we have an assigned. Okay. So, this is a 0 we have assigned, and now we come to the second row. Now, we again repeat the same steps. So, we in the first row we have made an assignment, in the second row there is a single 0 here, we make an assignment here. Okay. And then in the third row we have made an assignment, in the fourth we have made an assignment, in the fifth we have made an assignment. So, okay, so A is given job 1, okay, B is given job 2, C is given job 5, C is given job 5, D is given job 4. D is given job 4. Okay. So, we have this A is given job 1, B is given job 2, C is given job 5, D is given job 4, and the job 3 you can see here, job 3 is undone, job 3 is not given to anyone. So, job 3 is remains undone. Okay. It is not assigned to any no facility is assigned to this one. So, this remains undone. So, when we have an unbalanced problem, then we will add a dummy facility. Okay, like here we have added a dummy facility E and award 0 cost to all elements in its row. So, that the problem becomes a balanced assignment problem, and then we follow the usual Hungarian method to solve this problem and arrive at the solution. So, here we have considered a problem where due to some restrictions the assignment of a particular facility to a particular job is not permitted. So, in such cases we assign a very high cost to the corresponding cell, and that excludes this activity from the optimal solution. So, that is how we tackle such kind of problem where restrictions on assignments are given. Okay. So, that is all in this lecture. Thank you very much for your attention.